Hey guys, Mr. Backenberg here. In this video, we're going to look at implicitly defined functions.
So up until now, we've been dealing with explicit functions, which means they're in the form y equals some f of x. All of these functions have told you exactly what y is equal to, or we could say that they've been solved for y. So all the differentiation that we've been doing with those explicit functions has been explicit differentiation. But as we start to take a look at implicit functions, so a function such as y plus xy equals 4 is not an explicit function because it's not solved to have y all by itself. So we would say that this function is defined implicitly. Now, some implicit functions, but not all of them, can be rewritten explicitly, but that's not always the case. So if we looked at that function y plus xy equals 4 and we wanted to rewrite it explicitly, we'd be trying to solve to get y alone. On the left-hand side, I notice that both of those terms have y in it, so I could take out a GCF of y, and that would leave me with 1 plus x equals 4. And then if I wanted to get y alone, I would have to divide that 1 plus x over to the other side. So I would get 4 over 1 plus x as my y function. So now this has been rewritten as an explicit function. We've solved to get y alone, so we know exactly what y is equal to. But again, not every implicit function can be rewritten explicitly. Now let's take a look at this implicit function. We've got x squared plus y squared equals 25, and we're going to rewrite that explicitly. Now you might recognize this as the equation of a circle with a radius of 5. But anyway, our goal is to solve to try to get y alone. So the first thing I'm going to do is take that x squared and subtract it over to the right-hand side. So then this is going to say y squared equals 25 minus x squared. And then to get rid of the squared power on that y, we're going to have to square root both sides. Now when we do that, be careful. We have to remember to put a plus and a minus in front of the radical, and then we're not allowed to break down these individual pieces because of the subtraction happening between them. So underneath the radical, I'm going to leave it as 25 minus x squared. So this has now been rewritten explicitly. We solved for y, so we know exactly what y is equal to. Now, like we mentioned before, not every function can be written explicitly. So if we were looking at the function x cubed plus y cubed minus 9xy equals 0, we could try to solve to get y all by itself. I could subtract that x cubed over to the right-hand side, so then I would have y cubed minus 9xy equals negative x cubed. I could try to take out a GCF of y, but then I would still have stuff with y in it on the inside. So there's really no way for me to isolate y and get y all by itself. But even if you're not able to rewrite a function explicitly, you still can find a derivative using implicit differentiation. So here's the process on how implicit differentiation is going to work. One thing we have to remember is that we need to make sure that we're treating y as some function of x. So what we're going to do is derive both sides of our equation with respect to x. Now when we do that, because of the chain rule, every time we differentiate a term that has y in it, we have to attach the dy dx, because we have to remember that we're treating y as if it's a function of x. So anytime you do the derivative of something with a y in it, when you're doing implicit differentiation, you have to attach a dy dx to it. And then at the end, once you've done all of that, we're going to solve to get dy dx alone. So in this example, we're going to take the derivative of the implicit function y squared equals x. So when we do the derivative of this first piece, that's going to be the power rule, so we'll drop the 2 down, but then we'll have to subtract 1 from the power, so we just get y to the first power. Now this was a y term, so we need to attach dy dx to this, and then on the right-hand side, we're going to differentiate that x. And when you take the derivative of x, you just get 1. So that was our first couple steps. We took the derivative of each side, and anywhere we saw something that had a y in it, we attached dy dx. Now the last step is to solve to get dy dx alone. So we've got this 2y happening on the left-hand side. So we're going to have to divide that over to the right-hand side to get dy dx alone. So when we do that, we're going to get dy dx equals 1 over 2y. So this is the derivative of that y implicit function with respect to x. Taking a look at this example, we're going to find the slope on a circle. So we've got the equation x squared plus y squared equals 25, which is the equation of a circle centered at the origin with a radius of 5. And we're going to find the slope of that circle at the point 3, negative 4. So anytime we're dealing with slopes of a tangent line, that means we're finding a derivative. So we have to differentiate this implicit function. And again, we're going to take the derivative of both sides. So if we differentiate the x squared and use the power rule, that turns into 2x. If we differentiate the y squared, we drop the 2 down as a multiplier, so that becomes 2y, but then that's a y term, so we have to attach dy dx to that. And then when we differentiate the constant on the right-hand side, that just turns into 0. Now we want to go through and solve to get dy dx alone. So the first thing we're going to have to do is subtract that 2x over to the right-hand side. So then we get our 2y with the dy dx equals negative 2x. I want to divide that 2y over to the right-hand side. So I get dy dx equals negative x over y. So this is my derivative. Now if I want to find the slope of the circle at that specific point, I'm looking at this x value and this y value. Well, my derivative has both x and y in it. So I want to plug both of these values in the appropriate spots. So the x value from the ordered pair is 3. So we're going to go negative 3 on top. And then the y value from the ordered pair is negative 4. Well, if we have negative 3 over negative 4, then that just turns into positive 3/4. So 3/4 is the slope of that circle at the point 3, negative 4. One last example we're going to take a look at here. We're going to show that the slope, dy dx, is defined at every single point on the graph of 2y equals x squared plus the sine of y. So we're talking slope, so that means we have to do the derivative. So we're going to start by doing the derivative of both sides. When we differentiate this 2y, that just turns into 2, but that was a y term, so we have to remember to attach our dy dx to that. When we differentiate the x squared using the power rule, that just turns into 2x. And when we differentiate the sine of y, well, the derivative of sine is cosine of y, and that was a y term again, so we have to attach the dy dx. Now we need to try to solve to get dy dx alone. And what we should notice is that we have two terms in there that both have dy dx in them. So what we're going to do is gather both of those things on the left-hand side. So I'm going to subtract this cosine of y dy dx over to the left-hand side. That's all one term together, so when we move it, it has to move together. So then I get 2 dy dx minus the cosine of y dy dx equals 2x. Now, because both of those terms on the left-hand side have dy dx in them, we're actually going to factor that out as a GCF. So we're going to take the dy dx out of here, and then we're going to be left with 2 minus the cosine of y, and that's equal to 2x. Now, if I want to get dy dx alone, I have to divide this set of parentheses over to the right-hand side. So we're going to get dy dx equals 2x divided by 2 minus the cosine of y. Now we're trying to show that this slope, this derivative, is defined at every single point on the original graph. Now what we need to be careful about, since we're dealing with a fraction, is we're never allowed to have that denominator equaling 0. So let's investigate that 2 minus the cosine of y a little bit. Because it's on the bottom of the fraction, we don't want it to equal 0. So I'm going to set it not equal to 0. And I'm going to add that cosine of y over to the right-hand side. So this would say 2 cannot be the cosine of y. And what I want you to do is think about the unit circle. And cosines, when we're looking at the ordered pairs on the unit circle, are the x values. So what this is saying is we're not allowed to have any trig angle values where the x value on the unit circle would be 2. But if we think about what all of those x values and even the y values look like on the unit circle, the whole point of a unit circle is that the radius length is only 1. So the largest value that we're ever going to get for one of those x values is 1. So we never ever have to worry about this cosine value ever equaling 2. That's not possible when we're looking at doing things with trig in radians. So because that's not possible, then this derivative is defined for every y value and x value that we would ever want to plug in. That's going to be it for this video. Thanks for watching.